In this video, we're going to look at weak acid, strong base titrations. So we're still going to have a strong base in our burette, so our titrant is still going to be a strong base, but in our Erlenmeyer flask, we actually have a weak acid. And just like we did with the strong acid, strong base titration, we're going to just kind of work through an example. Do note that we expect our pH to be basic at the equivalence point, right? If we think back to our weak acid, strong base neutralization reactions, right? Because that's what we're doing here. At the equivalence point, I would expect that my pH would be basic, right? When I have equal amount weak acid and strong base, right? If I'm forming water and a salt, I would expect to have a basic pH. So I do want my pH to be greater than 7 at the equivalence point. So our example, we'll use similar numbers. Let's have 40 milliliters of a 0.1 molar acetic acid solution. And it's going to be titrated with we'll use 0.1 molar again, sodium hydroxide. So again, the first thing I would always do is determine the number of milliliters or what volume of base you need at the equivalence point. Even if the problem doesn't ask for that, I would do it. So volume of sodium hydroxide needed to reach the equivalence point. And again, because I have equal concentrations of my acid and my base, it is going to be equal volume. So we could just say 40 milliliters. I'm going to write down the calculation anyway, just because they're not always going to be equal. So I'm going to calculate my millimoles of acid and I'm going to do that by just taking my volume in milliliters, multiplying it by my molarity, which I'm looking at that as being millimoles per milliliter, right? Milliliters are going to cancel, and I'm going to have 4 millimoles. And again, if you want to write that out, like I'm not actually writing the units out, so you can't really see them cancel, but I have millimoles over milliliter, right? I have 40 milliliters. And then those guys are canceling. Again, if you prefer just using moles, make sure you convert 40 milliliters to 0.04000 liters, right? You need to do that conversion. What that means then is at the equivalence point, I'm going to have, this is acetic acid, I'm going to have the same number of millimoles of base. So at the equivalence point, we're going to have 4.00 millimoles of my strong base. Again, I'm using sodium hydroxide. The sodium ions are going to be spectator ions, right? They're not going to be important here. So I'm just writing sodium hydroxide as hydroxide. Usually I use asterisks. Not sure why I switched it to a star. I want the volume, so I'm now going to take my number of millimoles. I need to divide that by my concentration, right? 0.100 millimoles per milliliter, right? We need to divide so those units cancel. And I'm going to have 40.0 milliliters of sodium hydroxide needed to reach the equivalence point. So needed here, I wasn't being redundant, but needed to reach the equivalence point. Maybe we should add it. Just if we look back, needed for what? Needed to reach that equivalence point. All right. And again, I just find that number useful. So if you were given, calculate the pH at 20 milliliters of sodium hydroxide added, that's actually the half equivalence point, which is going to mean something to us as we go through the problem. And it's just a good idea to have those numbers. And oftentimes I ask for it anyway, but that is something I do like to calculate first. So we're now going to calculate the pH. And then our first one is going to be initially. So that means no base, right? 0 milliliters of sodium hydroxide has been added. And then because this is a weak acid solution, we're going to calculate the pH as you would for any weak acid. So you're going to set up an ice table, right? You're going to write your acid dissociation equilibrium equation. So calculate the pH. So you're going to write your acid dissociation equilibrium equation, ice table. You're going to use your Ka because you're writing your acid dissociation equilibrium equation. So just like you were doing in chapter 14, right? We give you a weak acid, I give you its concentration, I give you its Ka, what is its pH? You do need the Ka, I did forget to give that to you up here. My Ka is 1.8 times 10 to the negative fifth for acetic acid. So our ice table, and I'm going to do this pretty quickly. We've done this many, many times at this point. So hopefully you have gotten pretty good at it. Right? They're all aqueous except for my water, which is a pure liquid. We're going to have our initial concentrations, our change, and our equilibrium concentrations. Initially, my concentration of acetic acid, we go back up to the problem, is 0.1 molar. Water doesn't have a concentration, 0 and 0, minus x plus x plus x. 0.100 minus x. For equilibrium concentration, though, I am going to ignore that minus x because my Ka is less than 10 to the negative third, x and x. Right, we're now going to set those equal to my Ka. So concentration of hydronium ions multiplied by the concentration of acetate ions, my conjugate base, so x times x or x squared. And then 0.100 minus x, but because my Ka is small, I'm going to ignore that minus x. We're going to solve for x. So I'm grabbing my calculator. And I got that x is 0.0013. Let me put some units on there because I'm about to write concentration. And remember, x is my hydronium ion concentration. So taking the negative log of that number, I get my pH to be 2.88, 2.89 actually. So before any base has been added, all I have is a weak acid solution. We calculate the pH as you would for any weak acid. right? That involves writing my acid dissociation equilibrium equation, making my ice table, setting it equal to Ka, solving for X, which is hydronium, take the negative log of that to get my pH. Part B, we're going to now start adding base to it. So I'm going to have added, so how do we have it? We're to calculate the pH after 10 milliliters of our 0.100 molar sodium hydroxide solution has been added. So anytime we're adding acid to my base, I'm going to write that neutralization reaction. So we're going to write that. I have my acid. I'm adding a strong base to it. The sodium ions are spectator ions, so I'm not going to include them, right? We don't really care about those. I'm going to produce water plus CH3CO2 minus my conjugate base, so acetate ions. So again, I'm adding base to my acid. We're going to write that neutralization reaction. So that's our first step. I'm then going to make essentially my change table. So I started out with 4 millimoles of my acid, right? We calculated that earlier. If we go back up here, right? Millimoles of acid, 4. I do need to know the number of millimoles of base that I've added, and you can do that calculation first if it's easier, but I have 10 milliliters of a 0.1 molar solution, so 10 milliliters multiplied by 0.100 millimoles per milliliter is going to give me 1.00 millimoles of OH minus, so that's the number that's going to go here. Water, it's a pure liquid. I don't have to worry about that. And then this is 0. We're going to then subtract the smaller of the two reactants from both of them, and then we're going to add it to the product side. When we were doing our strong acid, strong base one, the only thing I had in products was water, but here I actually have something that is basic, right? My acetate ions will react with water. They are going to be important. So we do need to add it to the product side. So I'm going to subtract the 1, because that's my smaller of the two. And then I'm going to add it to this other side. So I have 3 millimoles of excess weak acid, right? I still have weak acid present. My strong base has all been neutralized. That goes to 0. And then I also have 1 millimole of my acetate ions. So then we just need to kind of look at this and say, okay, what do I have? Do I have a weak acid solution? Do I have a weak base solution? Do I have a buffer solution? Like, what's going on? And what I have, right, is a buffer. I have 3 millimoles of acetic acid. I also have 1 millimole of its conjugate base. So I have a buffer solution at this point. Right, we have both my weak acid. I'm just going to write HA because it might not always be acetic acid. I could give you something different. So I have both my weak acid and its conjugate base, A minus. So we do need to figure out our concentrations by dividing through by our total volume. So we'll do that. But then once I do that, we can either use our Henderson-Hasselbalch equation. We could write our acid dissociation equilibrium equation and use Ka. You could do this a couple different ways. I am going to use the Henderson-Hasselbalch equation. pH is going to be equal to pKa plus the log of the concentration of my base component over the concentration of that acid component. And then again, remember, these brackets, right, mean molar concentration. So moles per liter or millimoles per milliliter, right now I have the number of moles, right? I have my amount, not my concentration. So we do need to calculate that first. So let's do that. My concentration of acetic acid is going to be my number of millimoles divided by my total volume at this point in milliliters. So going back up to get those numbers, right? We started out with 40 milliliters of acid, so that's what's in my Erlenmeyer flask. And then at this point, we've added 10 milliliters of sodium hydroxide to it. So the 40 that I started out with, plus the 10 that we've added. So I have a total volume at this point of 50 milliliters. So working that out, I have 0.0600 molar for my concentration of acetic acid. My concentration of acetate ions, I currently have 1 millimole, right? It's in the same container as my acid, right? It's also in that flask. So I started out with the 40 milliliters. I've added 10 milliliters to it. So same volume, they're in the same container. So working that out, this is 0.0200 molar. So then those are the values that we're going to plug into our Henderson-Hasselbalch equation. I do need my pKa still. So my pKa is the negative log of my Ka, which is 1.8 times 10 to the negative fifth. Which comes out to be 4.74. And we can now plug everything in. So my pH is going to be equal to my pKa, which is 4.74, plus the log of 0.0200 molar over 0.0600 molar. And again, those molarities are just, they're going to cancel each other out in terms of units. Before I type that into that calculator, I just going to go back up here and look. Right, we started out with a pH of 2.89. I've added base to it, so I am going to expect a number that's larger than 2.89. Once I hit enter on my calculator, if it comes out smaller, I've goofed up somewhere. So 0.02 divided by 0.06, then take the log of that number, and then to that I'm going to add 4.74. And I get my pH to be 4.26. So we've added some base to my acid, not enough to neutralize it all the way, right? I have some acid left over, but I also have some of the conjugate base. So what I have is a buffer solution. Next point for us, I think we're on C. I should have just looked, yep, C. So after 20 milliliters of our 0.1 molar sodium hydroxide has been added. So 40 milliliters is the volume I need to get to the equivalence point, right? If we go back up to that calculation we did to begin with, right? That's where my millimoles of acetic acid are going to be equal to my millimoles of hydroxide that I've added. I'm less than that number here. I'm only at 20. So I do know that I still have excess acid. It's excess weak acid, but I know that's where I'm at the curve. I'm below my equivalence point. So we're going to do the same thing that we just did in part B. I'm going to figure out the number of millimoles of base that I added by taking 20 milliliters, multiplying it by 0.100 molar. I'm going to I'm going to write my neutralization reaction, set up that change table, and then look to see what's going on. So calculating the millimoles of base that we've added, 20 milliliters of base multiplied by its concentration. I'm writing the capital M there for molar, but remember we're using it as millimoles per milliliter. Milliliters cancel, and I have 2.00 millimoles of OH minus added. We're going to write our neutralization equation just like we did before, right? So I'm going to take my acetic acid, I'm going to react it with my base. And then I get water and my conjugate acid. We're going to set up our table. So I'm starting out with 4 millimoles of acid, right? That was what was in my Erlenmeyer flask to start with. We've not taken any out, we've not added any, it's still 4 millimoles. I've added 2 millimoles of strong base at this point. I'm not starting out with any acetate. And then limiting reactant, right? Where I was going to take the smaller of my two reactants and subtract that from both of them. And then add that to the product side. So subtract from the reactants, add to the products. I have 2 millimoles of acetic acid at this point. All of my strong base has been neutralized, and I also have 2 millimoles of my acetic acid. So again, I have a buffer solution. Right? The reason I know that is when I look at this neutralization reaction we just did, right? Everything that's not 0, that's what I'm going to look at. And I have acetic acid, and then I have its conjugate base. So I have a weak acid and its conjugate base, that's a buffer solution. So we can use our Henderson-Hasselbalch equation again to solve for my pH. Alternatively, you could write your acid dissociation equilibrium equation, make an ice table if you prefer that method, that's perfectly fine. I do need to convert these to concentration, and they're going to be equal to each other, right? I have 2 millimoles for both of them. They're in the same container, so the volume is going to be the same, so I'm just going to do this in one step here. So both of them are 2 millimoles, right? I have 2 here, and then I have 2 here. And then I started out with 40 milliliters. We've added 20 milliliters at this point, right? I'm getting that from here. So I have 60 milliliters total volume. And if you just want to write 60 instead of 40 plus 20, that's perfectly fine. I just want you to see where the number's coming from. And I have a concentration for each of 0.0333 molar. Plugging these into my Henderson-Hasselbalch equation, pH is equal to my pKa, which we calculated above to be 4.74, plus the log of my base concentration, the concentration of my base over the concentration of my acid. And then when we do the math, my pH actually comes out to be my pKa. And I'll show you this here in a minute. We don't actually need to plug that into our calculators. So if you were to, take this number and divide it by this number, you get 1, right? Same thing on top and the bottom. And then the log of 1 is going to be 0. It is. So 0 plus 4.74 is 4.74. And this is my pKa, right? So this point is actually called my half equivalence point. And this is another reason why I would highly, highly, highly recommend doing this calculation first, right? 40 milliliters is the amount that I need to get to my equivalence point. Half of that is 20. So at 20 milliliters, I am at my half equivalence point. My pH is always going to be equal to my pKa at the half equivalence point. So if I would have done this first, if I would have just looked at this and said half equivalence point, all I would have had to do is write this down. I wouldn't have had to do any of this work because my pH is always going to be equal to my pKa at the half equivalence point, because my concentration of my acid and base are going to be the same, which means this is going to go to 1, the log of 1 is 0, pH equals pKa. So again, if you recognize that, another reason to have the volume at the equivalence point to start with, you would save yourself a ton of work. So I actually want to write that down here. This is our half equivalence point. So what I mean by that is the volume of base that we've added, the volume of titrant that we've added is half the amount that you need to get to the equivalence point. So my half equivalence point, and our pH is going to equal our pKa at the half equivalence point. And that's always going to be true for us. Kind of redundant to write this, but our pH is equal to the pK at the half equivalence point, which can save you some work, again, if you recognize that. If you didn't know that 40 milliliters was your equivalence point, or the volume needed to get to your equivalence point, then you wouldn't know that 20 was half of it. Okay. We are on D. So D, again, we're calculating the pH after 40 milliliters, so we're at the equivalence point of my 0.100 molar sodium hydroxide has been added. So we're really doing the same thing. I'm going to figure out the number of millimoles of base that I've added. I'm going to write my neutralization reaction. I'm going to set up that change table, and then I'm going to look to see what's going on. So we already did this number ahead, but we'll just do it again. 40 milliliters of base, 0.100 molar for my concentration, so millimoles per milliliter. Milliliters cancel. And we have 4 millimoles of OH added. So we are at the equivalence point here. Right? We started out with 4 millimoles of acid. We've now added 4 millimoles of base. By definition, we're at the equivalence point. We had already said that our pH should be basic at the equivalence point for a weak acid, strong base titration problem. So we should expect a basic pH, right? When we're done with this, if it's not basic, we goofed up somewhere. We want to go back and check that. So I'm going to write that neutralization reaction. So my acetic acid plus my hydroxide ions going to water plus acetate ions. Same thing we've been doing. I'm going to put in those number of millimoles. So these are the same because we're at our equivalence point. Right? We started out with 4 millimoles of acetic acid. I've added 4 millimoles of sodium hydroxide. This starts out at 0. Subtract the smaller number from both. They're the same, so we're just going to subtract the 4. Add it to the other side. And then this goes to 0. This also goes to 0, right? Equal number of moles, so they're both neutralized. I don't have excess anything, right? If we go back up to these ones, here I have excess acid, right? This is 0. Here I have some left over. This was excess acid, right? Base went to 0. I have acid left over. Here I have equal amounts. So I don't have anything in excess, right? They both go to 0. I do have to add it to my product though, because acetate ions are basic. They are going to react with water, right? If it was just water, we could ignore it, but I don't have just water. So if I go over here, what I have, right, the only thing that's not 0 is a weak base. So this is a weak base solution. I don't have a buffer anymore. If I had a buffer, I would have to have both of these, right? I'd have to have both of these. I don't have that. What I have is only a weak base. So we're going to calculate the pH as you would for any weak base solution, meaning we're going to write our base dissociation equilibrium equation. We're going to make an ice table. We're going to set it equal to Kb. We're going to solve for X, which is my hydroxide ion concentration, and then figure out pH from that. So I have a weak base solution. We are going to solve, right, calculate the pH as you would for any weak base solution. So just like you did in chapter 15. I do need the concentration, so let's figure that out first, right? Right now we just have millimoles, so let's get that number. So my concentration of acetate ions is going to be the 4 millimoles divided by my total volume. So again, we started out with 40 in my Erlenmeyer flask, and so far we've added 40 milliliters of base from the burette to that flask. So I have 80 milliliters total volume. So I have a concentration of 0.0500 molar. Keep in mind this is a weak base, not a strong base, so I now need to write my base dissociation equilibrium equation. So I'm going to have my base. I'm going to react it with water. We're going to get hydroxide ions plus my conjugate acid, which I'm going to run out of room to write. So let's slide all this stuff over a little bit. I'm also writing it incorrectly. Oh no, I was writing it correct. Sorry guys. I'm used to having acetate on the side, but it's hydroxide ions and my conjugate acid, which is acetic acid. And then setting up our ice table. So my initial concentration of acetate ions is this number that we just calculated. Water is a pure liquid. I don't have a concentration, 0 and 0. We've done these a gazillion times, so I'm just going to do it quickly. Plus X, 0.0500 minus X, X, and X. I do need my Kb, right? I wrote a base dissociation equilibrium equation, right? Acetate ions are a weak base. I'm reacting it with water to produce hydroxide ions. So I do need my Kb, and I'm going to get that from my Ka. So my Kb is going to be Kw, which is 1.0 times 10 to the negative 14th. I'm just writing Kw instead, divided by my Ka. So that comes out to be, I'm typing it into my calculator right now, 5.6 times 10 to the negative 10th. So that number is going to equal my concentration of hydroxide ions, right, X, multiplied by my concentration of acetic acid, so X squared, over my concentration of acetate ions, which is 0.0500 minus X. But because my Ka or Kb is small, and it's actually smaller than that, to the negative 10th. Because my Kb is small, we can ignore that minus x. Solving for x, and I'm going to double check it here. I've made a few mistakes in the last couple of minutes. We don't want to make another. And I get 5.3 times 10 to the negative 6 molar, which again is my hydroxide ion concentration, right? If we go back up to our ice table here, X is my hydroxide ion concentration. So you can now divide that number into Kw to get hydronium ion concentration and then take the negative log of that. Or you can calculate your pOH, which is what I'm going to do, and then subtract that from 14. So negative log of 5.3 times 10 to the negative 6. I get 5.28. And then again, the reason, right, just we want to think about this, we're not done. Don't mistakenly circle that and tell me that's your pH, right? Remember, we're expecting our pH to be basic, and that is not basic, right? If that was my pOH, or sorry, if that was my pH, right? If this O wasn't here and you goofed up, that's not a basic number. We're expecting something that's basic. So don't forget to subtract it from 14. And when I do that, I get 8.72. At the equivalence point, I have a weak base solution, right? Remember, the salt from a weak acid strong base solution is basic. So we're taking that salt, right? We're writing our net ionic equation here, but I do have sodium ions floating around. They're just spectator ions, so we're not really concerned with them. So I'm writing that base dissociation, right, equilibrium equation, and using that to solve for my pH. After 60.00 milliliters of our 0.100 molar, sodium hydroxide has been added. So same sort of steps. I'm always going to calculate the number of millimoles of base that I've added. I'm going to write my neutralization reaction. I'm going to make my change table, and then we're going to look to see what we have. So I had 60 milliliters of a 0.100 millimole per milliliter solution. Milliliters cancel, and I have 6.00 millimoles of my strong base has been added. We're going to write that neutralization reaction again. I'm going to plug in my number of millimoles. So we started out with 4. So far I've added 6 millimoles of my strong base. We can ignore water, and we started out with 0 of my acetate ions. And then we're always going to subtract the smaller number from the bigger. So this time 4 is my smaller number. And then we do add it to this side. I am going to ignore that this time. I'll explain here in a minute. So this goes to 0, which makes sense, right? At the equivalence point, we've now added enough base to neutralize all of my weak acid. And then we continued to add base. So I now have excess strong base, right? We neutralized all the acid, but then we added more base. So excess strong base. So we're actually just going to calculate the pH as you would for any strong base solution. I do have a weak base over here, right? I do have 4 millimoles of acetate ions, right? And that is a weak base. So if you wanted to do the problem kind of complete, you would actually do two things. You would figure out the number of hydronium ions, or you could even do hydroxide if you want, that you're getting from this strong base. Then you would write your base dissociation reaction for this, just like we did up here. You would figure out, just like we did here, you would figure out the number of hydroxide ions that you're getting from that. You would add those two together and then figure out your pH from that. So we are getting hydroxide ions from this, right? I have excess strong base. This does react with water to produce hydroxide ions in a conjugate acid. So I do get hydroxide ions from that. You could then add them together. However, the ones from this strong base, or from the weak base, the ones from this weak base are actually going to be negligible. So we're just going to ignore it. Most of the hydroxide ions are going to come from the strong base. So even though we do have hydroxide ions from this, right? This is reacting with water to form hydroxide ions. The amount that we get from that is negligible. So we're just going to focus on the strong base, and we're going to ignore that second part. So excess strong base, we're going to calculate the pH as you would for any strong base. So I'm going to determine my concentration by dividing through by the total volume. I have 2 millimoles. We started out with 40 milliliters. We added 60 milliliters of base to it. So I now have a total volume of 100 milliliters. Which means my concentration of hydroxide ions is 0.0200 molar. Because this is a strong base, I'm going to determine my pOH. If you wanted, you could divide that into kW. And I got 1.699. I do want 3 significant digits, right? There's 3 here, so I want 3 after the decimal point. And then my pH is going to be 14.00 minus 1.699. And I get 12.30, which incidentally is the same number that we got when we were doing our strong acid, strong base titration with the same concentration. If the concentrations are different, then it's going to be different. But if I'm adding the same volume and I have the same concentration, right, after the equivalence point for both a strong acid, strong base solution and a weak acid or titration and a weak acid, weak base, let me say that again. For both a strong acid, strong base titration and a weak acid, strong base titration. So after the equivalence point for both of those, it's going to be excess strong base. So if your concentration and volume of the base is the same, your pH is actually going to come out to be the same. So I do want to draw a graph. I'm going to add some lines to our paper here, just because it's going to be easier for me to draw straight lines. I'll get rid of it after I draw it. I know it's more difficult to look at when I'm showing it this way, but I'm not very good at drawing straight lines. So we're gonna have pH versus my volume. So pH is gonna increase on my y-axis. The volume of base added is increasing left to right on my x. I might have said pH incorrectly. That's my y-axis, my vertical one. So pH versus volume of base added. And then my pH titration curve, that's kind of ugly. It increases kind of gradually and then more sharply and then kind of levels off again. So our points that we talked about, right? Our first one here was initial. So that's when we had 0 milliliters. And our pH at that point, if we scroll back up somewhere, keep going, was 2.89. So going back down, this would be 2.89. And I put lines on my paper so I could draw that straight, and then I still didn't. My equivalence point, just kind of guessing, is going to be somewhere in there. If we go down, that was at 40 milliliters. And then across, we had a pH, if I go back up, of 8.72. Remember that the pH at my equivalence point for a weak acid strong base titration is going to be basic, so greater than 7. And then we had two others. We had one that we did at 20 milliliters. That was our half equivalence point. And then we had another that we did at our at 10 milliliters. And I'm not going to include them in here because it's going to get kind of messy, but we could, right? If this is 0 and then this is 40, 20 would be somewhere around here. So over here, I would have 4.74. We also had 60 milliliters. If I included that, it would be somewhere, I don't know, about right here. So if we went up and then over, this would be 12.30. And I'm going to leave those off because I want to add to this. So we're going to have this as 0.1. 0.1 is going to be initial. That's going to be where I have a volume of 0. And I'm just taking off these specific numbers because I want to make this so it's applicable to more than just this specific graph. So I'm going to say that my pH is going to be greater than 7. I'm just going to write it that way. And then I'm going to get rid of that specific volume also. And I'm just going to put equivalence point. So number 1 is initial, where I've had 0 milliliters. I'm going to make a number 3 here at my equivalence point. And then everything between 1 and 3 is going to be number 2. So that highlighted part is going to be number 2. And then just picking a different color highlighter, everything after my equivalence point is going to be number 4. So number 1, and let's get rid of those lines. Number 1, so this was initially, it's just a weak acid solution. So again, you calculate the pH as you would for any weak acid solution. So we make an ice table, we use Ka. Because we're using Ka, we're writing our acid dissociation equilibrium equation. Solve for X, which is equal to our hydroxide ion concentration. So again, just as you would solve for any weak acid solution. Number 2 is a buffer solution. So anything between 0 milliliters of base added and the volume that you need to get to the equivalence point is going to be a buffer solution. I would highly recommend using the Henderson-Hasselbalch equation, but you don't need to. If it's the half equivalence point, pH is going to equal your pKa. And that's only at the half equivalence point. It's always a buffer between those 2 points, right? Between 1 and 2 on my graph. if you're at the half equivalence point, so the volume of base that you've added is half the volume of the base that you need to get to the equivalence point, pH is going to equal your pKa. And then number 3 is our equivalence point. It's going to be a weak base solution. So solve for the pH as you would for any weak base solution, right? We're going to use Kb. We're going to make an ice table. You're going to solve for X, which is going to be equal to your hydroxide ion concentration. And then number 4, it's going to be excess strong base. So solve as you would for any strong base solution. And it's always going to be that situation, right? Initially, it's always a weak acid. That's the only thing you have in that Erlenmeyer flask, and you've added no base to it. At the equivalence point, all of your weak acid has been neutralized by your strong base. All you have at that point is your weak base, right? Essentially your conjugate. And it's not even really a conjugate, it's just the anion from your salt, which happens to be basic, so a weak base solution. And then everything in between those 2 points is going to be a buffer, right? We have our weak acid, we've added some base, that base has been neutralized, we added it to the product side, that anion again is basic, so a buffer solution. And then always after my equivalence point, it's going to be excess strong base. I've neutralized my weak acid and we keep adding base to it, so I have excess base.